In this example, we're going to evaluate the integral of the natural log of x dx. So we've learned several integration techniques so far, but the first thing that you always want to do when presented with a new integral to evaluate is to think, first of all, if you know any just basic antiderivative formulas that you could apply. So by basic antiderivative formulas, I mean, for example, that the antiderivative of e to the x dx is e to the x. Things like that, just your basic formulas. But so far we have not memorized a formula for the antiderivative of the natural log of x. So we're going to have to use something a little more complicated, one of the other integration techniques that we've learned. So another very popular technique we've studied is the technique of u substitution. Now for that to work, I need there to be some expression u, and then its derivative du. I need both of those to appear in my integral. But in this case, I don't see that happening. If I were to let u equal the natural log of x, then du would be 1 over x dx, but I don't see that anywhere in my integral. So u substitution is not going to work in this case. Now the technique we just studied is called integration by parts. Now typically integration by parts, not always, but typically, is used on expressions that look like products. And in this case I don't really have anything that right off the bat looks like a product, right? I just have the natural log of x and I'm trying to integrate it. But let's try and apply integration by parts anyway and see where that gets us. So just to review, the formula for integration by parts is that the integral of u dv equals uv minus the integral of v du. So to proceed with integration by parts, the first step I need to do is I need to identify what I want u to be and what I want dv to be. So I'm picking these expressions u and dv out of my original integrand here. Now there's no rules about how to pick u and dv. There are some guidelines or some suggestions that work in most cases, but there are no just set rules for doing this, just like in u substitution. It just takes practice to identify patterns. But let's think about what would be helpful in this case. So once I identify u and dv, what I'm going to have to do is I'm going to then calculate du by differentiating u, and I'm going to calculate v by integrating dv. So knowing that gives me a little bit of constraint, right? Because whatever I pick to be dv has to be something that I'm able to integrate. Now in my case, I've got this natural log of x. I don't want to let that be dv because I don't know how to integrate it. That's why I'm going through all this trouble anyway. So then it looks like u is going to have to be the natural log of x. But I still need to put something for dv, and dv in this case is just going to equal dx. So your dx is always going to go with your dv piece, whether you have something attached to it or not. The dx will always be over here. Okay, so now I'm here. So to proceed, I'm going to go ahead and compute du. So I'm just going to take, this part is just like a u substitution. I'm just going to take the derivative of natural log of x with respect to x, and in this case that's going to give me 1 over x dx. Now over here, I've got dv and I want v. I'm going to integrate to do that. So here I'm just integrating dx, which equals x. I'm going to leave off the plus c for now, and we'll just put that in our final answer. So now that I've kind of filled out my little chart here, I can actually go ahead and rewrite my integral using this integration by parts formula. So I see that my original integral should equal uv. So if I look at my little chart, that's a natural log of x times x, which I'm going to write as x ln x, minus the integral of v times du. which in my case is going to be x over x dx. Now here I can simplify that integral a little bit, and it just becomes the integral of dx. Okay, and then I'm going to proceed. Well, actually, let me back up. Now, we know that what we've chosen for u and dv is helpful if when we get to this step, we have an integral that we can evaluate. Right, so here I've ended up with this new expression, and part of it is the integral of dx. And that's something that I can actually integrate. Okay, so this is good. Right, if you get to this point and you cannot evaluate this integral, then either integration by parts is just not going to work, or maybe you need to choose a different u and a different dv. But in this case, it looks like we've done well, right? I can evaluate the integral of dx. So let's do that. So this becomes x ln x, and the integral of dx is just x. So I get minus x, and then I just want to include my plus c. Okay, so what we've actually done here then is we've actually come up with an expression for the antiderivative of the natural log of x. In this example, we're going to evaluate the antiderivative, or the integral, of 3x e to the 2x dx. So this is a complex expression. I'm not going to just be able to use a basic antiderivative formula. I'm going to need some sort of special technique to evaluate this integral. So the first thing you might consider is u substitution, but it does not appear that that's going to be helpful in this case. So maybe the next thing on your list is this new technique we've learned, which is called integration by parts. Integration by parts is going to often be helpful when you have a product like this, right? So here I've got this 3x times e to the 2x. So let's try integration by parts and see how it works out for us in this case. So remember that integration by parts is for integrals of the form u dv. And what we can do is we can say that that equals uv minus the integral of v du. Now, to use integration by parts, what we have to be able to do is we have to identify what u should be and what dv should be from our original expression. And then from there, we'll compute du and v by taking the derivative and integrating respectively. Now, I've mentioned this before, but I'll say it one more time. There's no set rules for how to pick u and how to pick dv. It's going to be a little bit different for every problem, and you'll get better at it with practice. But there are some guidelines. There are some things that are usually true or usually helpful. And often, if you have any what we might call a polynomial or an algebraic expression, something with an x in it, or some power of x, like 3x or x squared or x to the 6th, often that's going to be a good choice for you. Not in every situation, but in a lot of situations. So let's try, in this case, letting u equal 3x, and we'll see how that does for us. Now, if u is 3x, then dv has to be e to the 2x dx, and that's good because that is something we can integrate. We need to make sure that our dv is always an expression that we are able to integrate. Okay, so from here, I'm going to take the derivative of u to get du. And in my case, that's going to give me 3 dx. And then I'm going to integrate e to the 2x dx to get my expression for v. And in this case, if I do that, and you could do this out to the side if you weren't sure, but that's going to give me 1/2 e to the 2x. Okay, so once I have my pieces, I'm going to rewrite my integral using the integration by parts formula. So the first part here is uv. Okay, so u times v here. I'm just going to multiply those pieces, which is going to give me 3/2 x e to the 2x. And then the next part is minus the integral of v times du. So in my case, that looks like it should be 3/2 e to the 2x dx. And I'm going to rewrite this just slightly by bringing out this factor of 3/2 in front of my integral. So I have 3/2 times the integral of 2 to the x dx. Now, if I've made helpful choices for u and dv, this integral here in my new expression should be something that I can evaluate. And in my case it is. I've got the integral of e to the 2x, which I actually just evaluated a second ago. So then I can finish out the problem just by evaluating that integral. So then if I evaluate the integral, I've got my 3/2 out front, and then it's going to be times 1/2 e to the 2x, and then I have my plus c. So then in the end it looks like I get 3/2 x e to the 2x minus 3/4 e to the 2x plus c as my final answer. In this example, we're going to look at the integral of x cubed times the natural log of x to the 4th dx. So initially, this problem looks like it might be a good candidate for u substitution. Because I see that I have this x to the 4th inside the natural log, so maybe I want to let u equal x to the 4th, and then du would be 4x cubed dx, and I have an x cubed, so I could make this work. But the only problem is what I'm going to end up with is I'm going to end up with a natural log of x inside my integral. And we don't have any simple formulas for that. Now, just a second ago, we did see that you can take the derivative, you can integrate the natural log of x. And to do that, we used integration by parts. So it's possible, but it's not just a basic, straightforward formula. So maybe instead of u substitution, we want to try something else. And what we could try is actually integration by parts. And this will be good practice for integration by parts. So let's do that. So once again, the formula for integration by parts, I have the integral of u dv, and that equals uv minus the integral of v du. Now before I actually dive in and start picking out my parts, I'm just going to do one little thing to rewrite this just a bit to make it a little easier to deal with. I've got this natural log of x to the 4th. I can take that power of 4 inside the natural log and make it a coefficient. And that's just a property of natural logs. So if I rewrite this, I'm going to have 4x cubed times the natural log of x dx. Okay, so from this step then, let's go ahead and pick out what we want u to be and what we want dv to be. Okay, so keep in mind that whatever we pick for dv, we're going to have to integrate it. And then whatever we pick for u, we're going to have to take its derivative. Now we've said in past examples that it's often helpful, or it often works out well, to let u equal any powers of x that you might have. So for example, letting u equal 4x cubed would be helpful in a lot of examples. But it might not be the best choice in this example. And that's because if I let u equal 4x cubed, then my dv is going to have to be the natural log of x dx. But that's a little tricky to integrate, right? We have to actually use integration by parts to integrate the natural log of x. So we're going to have a fair number of steps involved there. So let's see if instead we can do this the other way around. Maybe we can let u equal the natural log of x and let dv equal 4x cubed dx. So let's see if that works for us. So if I let u equal the natural log of x, I want to take its derivative to get du. So that's going to be 1 over x dx. And then I'm going to integrate 4x cubed dx to get v. So that should give me x to the 4th. Okay, so let's rewrite our expression. So u times v, well that's x to the 4th natural log of x minus the integral of v du, which in my case is x to the fourth over x dx. So if I simplify that, I have x to the fourth times the natural log of x minus the integral of x cubed dx. So it looks like our choices actually worked out really well in this case because I've ended up with the integral of x cubed dx, which is really simple to evaluate. So if I finish this out, I've got x to the fourth, natural log of x, minus, and then this will give me 1/4 x to the fourth plus c. Here we're going to look at the antiderivative of the inverse tangent, or the arctangent of x. So first of all, let's keep in mind that we don't know a basic formula for this. We know a formula for the derivative of the inverse tangent, but not for the antiderivative. So we're going to have to be a little more clever in our techniques here. So we have a few common options, a few common integration techniques available to us. One of the more common is u substitution. That doesn't appear like it's going to be helpful in this case. I don't see some expression u whose derivative also appears in this integral. So another common, often helpful integration technique is integration by parts. And right off the bat, it maybe doesn't look like that would be helpful in this case because there's not an obvious product here. But let's see if we can make that integration by parts work. So here is my integration by parts formula, which hopefully you've seen several times by now. And we know from our previous practice that what we need to do next is we need to identify what we want u to be and what we want dv to be. And whatever we pick for u, we're going to have to take its derivative. And whenever we pick for dv, we're going to have to integrate it. So we should keep that in mind as we make our choices. So I certainly don't want to pick the inverse tangent to be my dv because I don't know how to integrate it. That's what I'm trying to do to start with. So then it seems like, just by process of elimination, that u is going to have to be the inverse tangent of x. So then what does that leave for dv? Well, dv is just going to be dx. Our dx always goes with our dv. So from here, let's try to compute du and v accordingly. So to compute du, I need to take the derivative of the inverse tangent. And you probably haven't seen this in a long time, but you did learn this formula at one point. The derivative of the inverse tangent is just 1 over 1 plus x squared, dx in this case. And then for my v, I'm going to integrate dx, which is just going to give me x. Okay, so let's see what happens when we rewrite our integral using these pieces. So first I've got uv, which in my case is going to be x times the inverse tangent of x. And then I've got the integral minus the integral of v du, which here is x over 1 plus x squared dx. Okay, so I've got this new integral now that I want to evaluate, and hopefully I can, right? If I've made good choices up here, then this integral should be something that I am able to evaluate. This integral looks, though, maybe a little more complicated than the ones we've seen in past examples, but if we think critically, this is something that we can evaluate. And we're just going to have to use another integration technique to do this. And actually what we're going to want to use here to evaluate this integral is u substitution. Okay? So instead of using the letter u, since I already used it above, I'm going to use the letter z, but it's the same idea. So it looks like maybe it would be good to let z equal the denominator of my fraction here, this 1 plus x squared. And the reason that's good is because when I compute dz, the derivative, it's going to give me 2x dx, and I see that I have this x dx on top. So I can rearrange this a little bit and write it as 1/2 dz equals x dx. Okay, so now I'm all ready to make my substitution. So let's just work on this integral for a second, and then we'll carry down this other part of the expression. So if I make my substitution, this is going to turn into a factor of 1/2, and I can put that out front of my integral. And then inside, I'm just going to have the natural log, or sorry, I'm getting ahead of myself here. I'm going to have 1 over z dz. Okay, and I'll bring down this x inverse tan of x. Okay, so then if I evaluate that integral at this point, I'm going to get minus 1/2 natural log of z plus c. And then as my last step, I just want to substitute so that I'm back in terms of my original variable. So I'm going to get x inverse tan of x minus 1/2 natural log of 1 plus x squared plus c. Notice that I dropped my absolute value symbols. I can do that in this particular case because 1 plus x squared is always positive. All right, so this is my final answer. And this expression here is actually the antiderivative of the inverse tangent of x.